Okay, let's talk about Euler's method. Euler's method deals with finding not necessarily solutions to differential equations, but if we're given a point, we're going to use a numerical method, in this case Euler's method, to evaluate the function at a different point. Okay, so we look at this and you're like, wait a second, if I have a differential equation and I have some initial value, why can't I just separate and solve? Why can't I just solve for y? If you want to know f of 1.4, just find the function and plug in 1.4. And so you look at that and you're like, wait a second, I can't separate that. I can't subtract y. That doesn't do anything for me. I can't divide by y. I can't manipulate this algebraically. Well, what we have here is, at least in an AP, Calc AB or Calc BC, this is a not really in our separable differential equation wheelhouse. So we can't do it. We can't separate. We can't solve for y. If we could, well then we would just plug in 1.4. So the question is, how do we use Euler's method to still give us a really good idea of what the function is at 1.4? Okay, and this is all it boils down to. This is the entire method. All it's saying is that dy dx is pretty much equal to a delta y over delta x. Right? This is the instantaneous derivative, and this is the rise over the run that's over an interval. They're not exactly the same, right? This is over an interval, and this is at a point. But we can use those two to say what Euler's method says. And so take that, and all it says is that delta y is pretty much equal to, moving the delta x over the other side, is pretty much just the derivative at a point times delta x. Again, we're taking the instantaneous rate of change and multiplying it by that run to get the appropriate rise. And so if we just did that enough, we'll get there, okay? This, of course, is just the derivative, and this is what we're going to refer to as the step size. That's how much we're stepping to the right or left and finding something. Again, we're using the derivative at a point. Well, I can find the derivative at a point, and I can move a little bit along to the right, and if you tell me that you're moving to the right, I can multiply by the slope then to tell you how much to move up. Again, it's pretty basic in terms of where this derivation comes from. So let's kind of go through two examples. Okay, if you know that 1, 2 is a point on the slope, and you want to know then what 1.4 is. Okay, so they have to tell you this. They have to give you this, give you what they want, give you the differential equation, and they have to tell you the number of steps. The number of steps will then tell you what delta x is. Again, look, I'm going to go from 1 to 1.4 in 2 steps. That tells me that delta x is 0.2, meaning the step size. I'm going to move over 0.2, and then I'm going to move over another 0.2, and then I'll be where I want. Okay? So we just do the same thing twice. So I'm going to write this again. Delta y is going to equal dy dx times delta x. Okay? And so let's start with the point 1, 2. So what is delta y? Delta y is going to be the derivative at 1, 2. Well, the derivative is 2 times x plus y. 2 times 1 plus y of 2, that's 4. So the derivative is 4. My delta x is 0.2. And so then I get a 0.8 for my delta y. And I start all over. I have some new point because 1, but then I moved over a delta x of 0.2, so then my new point is 1.2, comma, well, I get a delta y of 0.8, so my new y value is 2.8. And I've moved over, basically using the slope to move over, and now I know this point. And so I do the whole thing again. The new delta y is the derivative at that point. Well, 2 times 1.2 plus 2.8 is 5.2 times delta x of 0.2 is going to give me 1.04 for my new delta y. And I get another new point. But my new point now is 0.2 over from that, 1.4, and my delta y, I add that, right? Delta y is the change in y. Add that to my 2.8 to get 3.84. And that's another point. But look, That's exactly the point I wanted. I wanted f of 1.4, and so then your answer here is 3.84. I can't solve this differential equation, at least by any normal method in the separable differential equation category, right? I'm talking about the AP level. Now, if you're in college, again, maybe even a separable one, you would talk through the solution to something like this. But on the AP level, both AB and BC, this is in the non-separable category. But we can still find solutions using numerical methods. In this case, we're using Euler's method. This is Euler's method. Okay, we'll do the same thing over here. Okay, let's find the first delta y. We know that delta y is really, really close to being the same thing as the slope times delta x. They're not really equal, but if our steps are small enough, then that's going to be just fine. Okay, so we start with 4, 1, and we want f of 3.6. Okay, they have to tell you to take 2 steps, and on the AP they almost always say 2 steps. I can't even think of an example in like the last 20 years where you haven't taken 2 steps. So if you want 2 steps to go from 4 to 3.6, then you're going to have a delta x, and sorry about that, make sure you know that's a negative 0.2 for your delta x, right? We're going to go from 4 to the left to get to 3.6. We have to use a negative delta x, which is fine. Okay, so we start out with 4, 1. What's the slope at 4, 1? Well, 4 minus 1 is 3. So that's 3 times negative 0.2, and that's going to give me negative 0.6. But then I get a new point. My new point is going to be 3.8. Again, I started at 4, and I went to delta x of negative 0.2, so I went to the left. And then my delta y is negative 0.6. I started at 1, and now I'm going to be at 0.4. That's my new point. And then I do the whole iteration again. I find the new delta y. Okay, so I take 3.8 and 0.4, and I come up here and I find the slope at that new point. Well, the slope is just x minus y, so it's just 3.8 minus 0.4, and I just get 3.4 for my slope, right? Slope times delta x of negative 0.2, and I get negative 0.68 as my new delta y, and that's going to give me a new point. My delta x was negative 0.2, so I get 3.6, and I'm going to go down by that. So 0.4 down by this is going to be negative 2.8, and I get my new point. But again, that was the goal. I have evaluated the function at 3.6 without ever having the ability to actually find the function. I just found an approximation. And if you want the approximation better, if you want these things to be, kind of closer to being equal, well, then you just got to make your step size really small. But this is really easy for an Excel program or probably your graphing calculator, certainly a computer, to do something like this. They can make the steps like 0.01. And so then you're using the derivative at a point and moving over just slightly, and then finding the new derivative at that point, and then moving over slightly. And so it's like you're constantly using the slope field to figure out what the new y value is. And basically you can get any y value you want on this function. All you had to know was the rate of change of the function or some differential equation. You need to know some starting value, and then you got to have some goal. What do you want to do? On the AP test, this is always what you're given on a question like this. You are given the differential equation. You're given some initial point, what you want, and they have to tell you the step size. Because if they don't tell you the step size, how do you know what delta x is going to be? Okay, those are the 4 things they would give you. And then you would do 2 steps. And actually, even on the AP test, most of the time it's a non-calculator question. So you're going to have to be able to bust up these decimals and fractions, kind of just like I did.